before we get started, I request everyone to keep their cameras and microphones turned off throughout the program. So it's my honest request to every one of you. A very good afternoon to everyone. I, Ankan Bhattacharyya, the Secretary of the Geological Institute, on behalf of all the committee members and our department, welcome you all to this 45th Extra Memorial Lecture. The last 1.5 years have been drastic for all of us. However, we have all fought back hard and have continuously tried to adapt to this new normal. The Extra Memorial Lecture holds an emotional place in the heart of all students of this department. This event sparks nostalgia among everyone, taking them back to their old college days. Some present here either used to organize this event in the department or had the chance to witness and learn from the most caring and beloved teacher, late Professor Santosh Rai. Yesterday, we celebrated Teachers' Day, and today we are here at the 45th Memorial Lecture dedicated to the memory of a teacher who inspired many and immensely contributed to this department and the field of geology as well. We might not be physically present in our institute, in our beloved department, yet the legacy must be continued. So here we are, presenting you all today's memorial lecture in an online mode. Without taking much time, I would like to request our very own head of the department, Professor Gautam Ghosh, and President of the Geological Institute, to address the audience and speak a bit about our highly regarded Professor Santosh Rai and introduce our speaker as well. Over to you, sir.
Thank you, Ankan. Can you hear me? I am clear?
Yes,
Yes,
sir.
Enough? Okay, okay.
Yes, sir.
Thank you, thank you. Okay, good morning and good afternoon, everybody. Professor Sumit Chakraborty, the distinguished members of the Geological Institute, my colleagues, friends and dear students, I welcome you all to the 45th Esra Memorial Lecture organized by the Geological Institute, the student body of this department. As Ankan previously said, with the COVID-19, this pandemic is still continuing and in a very disruptive manner for 2 successive years. It is hampering all our normal practices. And hence, the members of the Geological Institute have found no other way but to organize the 45th Esra Memorial Lecture like the last year in an online platform. However, though these are the disadvantages of this pandemic, to look at it in the other way, this pandemic and this online mode has also opened up new opportunities to us. And as a result of this, I think we are fortunate to have Professor Chakraborty amongst us today for this lecture, which would not have been possible otherwise. At the beginning, and going in the traditional way, I wish to pay tributes to the loving memory of late Professor Santosh Kumar Roy. Though I am not a direct student of Professor Roy, the legacy of Professor Santosh Kumar Roy, his teaching and his teaching methodology were passed on to us by our teachers, who were immediate disciples of Professor Roy. And what I gathered from them, from their reminiscence about Professor Ray, I think can be expressed most appropriately in Bengali as সেই শিক্ষক যিনি মনের জানলা খুলে দিতে পারতেন, ছাত্রদের চিন্তা করতে শেখাতেন, ভাবতে শেখাতেন. Hence, though a day has passed after the Teachers' Day, I feel proud to be able to pay my homage to Professor Ray, the teacher of all teachers, on this event. Professor Ray joined as a faculty of the Geology Department of the West Royal Presidency College in 1944, and from the very beginning, he established himself as a brilliant teacher and researcher who could inculcate great enthusiasm amongst his disciples. He took over the stewardship of the department after a few years and revolutionized teaching and research activities of the department through his sincere and untiring efforts. He was ably assisted by a band of dedicated teachers in the department those days. However, the man who held the most profound influence on students was none other than Professor Roy. His erudite teaching became a myth amongst all later generation of teachers and students. His excellent ability of out-of-the-class counseling generated great interest among students in various branches and fields of geology, and many of his disciples eventually became pioneers in their respective branches in their later careers. He always used to encourage students to venture into new fields, to think and work outside the regular and habitual course of activities practiced by others, and in the process entrusted a profound sense of self-belief amongst his students. Since his untimely demise in the year 1976, the department every year organizes this lecture in his fond memory, which is delivered by an eminent scientist. On this day, by reconciling his works and his memories, we vow to follow his footsteps, of not to mesmerize students by our teaching, but to drive these young and fresh minds to newer quests, to get feedbacks and enrich ourselves in the process. This year, we are privileged to have Professor Hashumi Chakraborty amongst us. Professor Chakraborty is one of the most accomplished names in the fields of physico-chemical mineralogy and petrology. His primary research interest is to study timescales over which geological and planetary processes occur. For this, he uses the tools of physical chemistry and more precisely the application of kinetics, diffusion modeling, and thermodynamics. Professor Chakraborty has played an active role in the progress of the field of diffusion chronometry. His work involves theoretical modeling, experimental measurements, analytical chemistry, and field work. He has gathered remarkable field experience from different parts of the globe, and his work focuses on high temperature processes which are operative inside the Earth and other planetary bodies. He has also worked with meteorite samples. He is an alumnus of our department and obtained his PhD from the University of Arizona. Presently, he is a professor of physico-chemical mineralogy at Ruhr University, Bochum. His commendable works in the field of mineralogy geochemistry have made him the recipient of the Dana Medal in 2016 from the Mineralogical Society of America. Presently, he is the Vice President of the Geochemical Society and Associate Editor in charge of the Interior of the Earth for Earth and Space Chemistry. He has been the elected Fellow of the Mineralogical Society of America and Fellow of the Geochemical Society and the European Association of Geochemistry. So with this brief introduction about Professor Ray and Professor Chakraborty, I would now like to invite Professor Hashumi Chakraborty to present his speech on today's topic, which is the time scales of geological processes in the Earth, continuous or stop and go. So over to Professor Chakraborty.
Thank you very much, Gautam. It's a particular privilege and an honor for me to be here at the Esra Memorial speaker because I remember exactly the time when I was a student and I was sitting on the other end of it, and I never thought ever that I would end up on the other side of the table here today. So it feels particularly strange. Now, I joined Presidency College in 1976, exactly the year that Professor Rai passed away. So I never had the fortune of meeting him. But like many others here, I've been taught by students of his. And so in a way, I'm a grand student of Professor S. Roy, if you will. So that the memory of those days becomes particularly clear to me when I see some faces that I saw on my first day in college. So I saw DM, Dhruva Mukhopadhyay here, and I have to say it doesn't look a whole lot different from what he did when I saw him in 1976. So, and it's also particularly timely that we have this lecture today, a day after the Teachers' Day, and so I'd like to begin the talk with paying my respects and gratitude to my teachers who are here. So getting to the talk here today, the title is Timescales of Geological Processes, Continuous or Stop and Go. So to introduce the theme, let me just change the screen here. Yeah. So I should say I don't see anybody here, so somebody has to speak up because I don't see myself or anybody here. Now, one of the greatest debates in earth sciences is the debate between uniformitarianism and catastrophism. So on the uniformitarianism side, there were famous names like Hutton and Lyell. And on the catastrophism side, there were many people involved, for example, continental geologists like Cuvier and Élie de Beaumont. Now, the debate had two real components in it, actually. So one was whether processes that occur today, processes that we see today, were also the same in the past. And that was the part that Hutton and Lyell established, of course, and with slight modifications. So it's the not the exact processes with their intensity, but the same physical principles applied in the past as they do today, and helps us to read the rock record. Now, there's a second component to that debate, and that was if you have long timescales, do the processes themselves last very long? Do they go on for very long timescales, or do you have things that happen on very short timescales, so continuous or episodic? Now, however the debate may have played out, we know that there are catastrophic events. We know that there are volcanic eruptions. We know there are earthquakes. We know there are meteorite impacts that caused profound changes in the Earth's history. So the question is, how do they play out together? So to get to that, now I am a high temperature petrologist, so I'll look at high temperature processes, and this is sort of the image of a process that we had when I was a student. So you have some event that's happening at high temperatures, and the idea was to try to find the condition at which the rock formed. So that would be this blue circle here. And then after that, we assumed that things cool down at some rate to get to the surface today, and we didn't know too much at the time, so assumption was some constant cooling rate, slope on this temperature timeline in a straight line. Now, as time went on, techniques developed, and we found ways to find not just the peak temperature, but several points along the cooling history, along the cooling path. So these are these other blue circles here. And so it could be a different temperature, a different time, different dates. And so once we had those other points, the idea was to connect them using a straight line, or in this case, a smooth curve. And what you see now, in contrast to the first one here, is that there's a change in the cooling rate, but it's still a very smooth curve. Now, the question is, what if the evolution is something like this over here? So if you have a peak temperature, there's nothing that says that a geological process must follow along a smooth curve like that. It could go in pulses, okay? And in that case, you have an event, which is this high temperature event that lasts over a long time, shown on this red line at the bottom. But along this event, you have various episodes that are pulses that last a short time. And if that were to be the case, the problem is that this is how we are determining it, right? So we have temperatures and time information at certain points that we can determine. And if these are these two blue points and we connect those by a smooth line, we don't know in between if there's a yellow spike like that, okay? And so the question really is, can we have tools to explore what the evolution looks like in a continuous pattern rather than looking at individual points and connecting the dots. So that's what I'm going to try to talk to you today about. And as an example of reading that rock record, I've picked out one particular set of samples from the Coorg Massif in South India. This is the next section of slides would be based on the PhD thesis of Champriti Boschak, which he finished in Ruhr University in last year, 2020. So now the left side of the diagram shows you the regional geological history, regional geological map of the area, and there are controversies related to that. I have it here because in international talks I need to introduce where Coorg is. It's up here in the left top corner of the block and enlarged here on the right-hand side. Now, for the purpose of this talk, the results I show you do have regional geological implications, of which I'm not an expert. They do have tectonic implications, actually profound tectonic implications, but I'm not going to talk about those today. What I am going to talk about is just about this aspect of reading the rock record. And I'll take you through one set of samples from this Coorg Massif, which come from these regions, the stars that are shown around you. So as you see, it's kind of the Coorg Massif and it's boundary. Okay, so what you do is you go to the field, collect samples. Now I'll be dealing with mafic rocks. So what you see here in these two images are you have nice, good outcrops. So you can go and collect rocks there. As you see here, already in the field, we started sort of distinguishing them into two types, Group A and Group B. And the difference is in Group A, you see some light-colored veins in the rocks. In Group B, you don't see them. They're more massive. And I'll show them in more detail in the next slide right away. Okay. There are more details of those rocks. And three of these pictures are from samples from Group A. And one on the bottom right is from Group B. What you see here now very clearly are those light-colored veins. These are plagioclase-rich veins. These are not much quartz in them, but the host is the mafic rock. And what you see on the field scale already is that the garnets in these mafic rocks are kind of concentrated close to the light-colored veins in these rocks. And you also have garnets in the Group B type, where you do not have any light-colored veins, and they're just spread out in different places. Okay, so if you go and do geochemical analysis of that, and this is just a section of the kinds of geochemical data we have, you see the difference carries on there. So it's not just something that looks a little different in the field. There are real differences between the chemistry of these two groups of rocks. So the Group A rocks are in blue, the Group B rocks are in orange. I'm just showing you again a few different chemical parameters just to show the point that in trace elements as well as in major elements, there's a clear distinction between the Group A and the Group B rocks. So the light-colored veins are somehow related to this chemical distinction there. And what that means for us today is that the chemical reactions or the signatures that you see in these rocks are going to be different, even though they have very similar mineralogy. Okay, so that's the classification that Chakraborty finally came up with. She focused on the garnetiferous rocks, there were mafic rocks without garnets as well. We didn't deal with those. And within that, the group A and the group B have distinctions in bulk chemistry, particularly in the magnesium content of the rocks. So now this particular slide is really designed more for the students. So I request more senior people to bear with me as I go through this here. So this is now a thin section from one such rock where you have autopyroxene, clinopyroxene, plagioclase. Now you can use the composition of these minerals to get the temperature at which these formed or they're equilibrated. And the way you do that is you measure for example, the iron and magnesium content of these two minerals. So this would be now iron would be the mole fraction of iron in mineral A. Let's say that's the autopyroxene divided by the magnesium content in autopyroxene, and then you take the magnesium and iron in clinopyroxene, you form such a ratio called Kd, and if you plot the logarithm of that against the inverse temperature, so your temperature is increasing towards the left, this is high temperature, right, low temperature is to the right, then the Kd is a function of temperature. So what that means is if you go and measure the compositions in such a set of minerals, you can go and calculate this function Kd. You can go and look up the ln Kd on this axis, go to this calibration curve. This is this purple line, and that would give you a temperature that you can read off from the curve. So you can do that to determine temperatures, and something slightly different but very similar in principle also gives you the pressure or the depth at which these things equilibrate. So let's try to do that with one of these sets of rocks here. So this is now the same rock actually that you were seeing before in the field with the light colored veins. That's the plagioclase rich veins in with garnet forming, these blue things are garnet forming very close to the vein. And you can look at that and you can look at the inclusions in a garnet to define a reaction where garnet forms from autopyroxene, clinopyroxene, and plagioclase. These were the primary minerals in this mafic rock, along with quartz. And if you do all the chemistry with that, you come up with a temperature of about 800 degrees and a pressure of about 11 to 13 kilobars, quite high. And we call that M1. Now, sorry. Yeah, I hope.
No, sir, it's okay. It's okay. You can continue.
All right. So now you see the subscripts here. This is because, as you will see very soon, there are different generations of these minerals that form in this rock. And so the first one of them, we call them garnet 1, and OPX, CPX, and plagioclase M stands for melt, and so forth. So there'll be subscripts. I won't bother with them too much in this talk anymore. So after this garnet has formed, you see second thing that happens. And this is now on the bottom, we have a larger scale picture. Now this is a small scale feature, so you don't see that very well in a microscope in a thin section. So this is now looking at a backscattered electron image. You see that near the rims of the garnets, things are breaking down, and that's zoomed up here. And what you see is garnet 1 breaking down, reacting with quartz to give you autopyroxene and plagioclase. And that gives you a temperature of about a little higher, about 850 degrees centigrade, and pressure of 10 kilobar, just slightly lower. So after you form that, what you see is that a second garnet forms in the rock. And this, you know, it's a second garnet because you have this garnet 1 here, and on top of that, you have a rim of this garnet 2 that forms on this. And this is a very porous, patchy garnet 2. Now, in the rock, you find also individual grains of this garnet as well. But because you have this relationship, because you know that this garnet 2 is growing on top of garnet 1, you know it's later. And through the inclusions and everything, you work out a somewhat more complex reaction where a hydrous mineral such as antipolar biotite reacts with clinopyroxene plagioclase to form garnet and other minerals and in its water. And finally, you see that the garnet 2 itself reacts with things like biotite, but also breaks down, and there are evidence of that as well. And that's just the reverse of the reaction that formed garnet 2, and that happens kind of at a lower temperature at 590 to 610 degrees centigrade. So you have a series of temperatures and pressures that you can work out that this rock has gone through. So these are your blue circles on the diagram, if you will. And you can also confirm that with similar analysis from other groups of rocks. So group A1 was one of those kinds of magnifics, and that gave you this particular history. But if you go and look at group A2, you see, like I said, different reactions, different behavior, but you can also do the thermogrammetry with them, and then you get the same sort of behavior. Now you see here it's about 780 to 800 degrees centigrade, but the pressure is quite uncertain, and you'll see that in next diagram. So here it gives you 8 to 10 kilobar, there's 11 to 13 kilobar, so the depth remains quite unconstrained. Now, if you take all of those, you can also go and calculate phase equilibrium for these things in using thermodynamic databases. So the databases that were used are shown here, mainly the Holland-Powell database. And again, the two different phase diagrams are for two different bulk compositions that you have. And for each one of those, you have those temperature and pressure coordinates from analyzing their compositions, and you get M1, M2, M3, M4, and so forth. And they seem to fit quite nicely with what you get from the phase diagram as well. So you get a consistent picture out of that. So you put them all together in a pressure-temperature diagram, and these are sort of the three overall stages that you get. So there are different histories in M1, M2, M3 recording individual rocks, but if you group them together, you see one big gray patch here, that's one stage, another big gray patch here, and the third one down here. So the question is, when did all of this happen? What was the age of all of these things? So it turns out we can determine the age of those things. So this is now using, because you have different kinds of garnets, you can use lutetium-hafnium dating of garnets, or you can use uranium-lead dating of zircons. And those give you quite distinct age populations. So the highest pressure temperature thing, now you see this thing on the pressure axis, this gray bar is quite large because of that large uncertainty between somewhere between 8 and 13 kilobars. We don't really know very well, but we know it's high temperature, then a somewhat lower temperature, and then much lower temperature here. So that's quite clear. And this one here is 3.1 billion years, so that's 3,100 million years. And this one right below is 2.4 billion years, so that's 2,400 million years. So you're going from Archean to the Archean-Proterozoic boundary. Now, the thing that you would do conventionally is something like this. You go and connect all of these dots with a smooth line. And what that would tell you in terms of the tectonics is that between about 800 degrees to 700 degrees, it took a very, very long time to cool down. So 700 million years or so. And that would be the image that you get by connecting the dots. But now comes the point of saying, can we do anything better than just connecting the dots? Can we see what's going on in between here? So to do that, I need to spend some time on this slide. And I'll try to take you through what goes on in such a mineral, in a rock, in more detail. So this is now back to our orthopyroxene-clinopyroxene pair, where I said that you can measure the composition to get that KD, and that gives you a temperature. So for example, if it forms at some high temperature, there'll be some composition of the orthopyroxene, some composition of the clinopyroxene. You can plot them up on such a concentration distance diagram. So this is now high. This red line here is the high concentration, let's say, orthopyroxene here. And then the interface after that, the same. This could be something like magnesium, for example. In clinopyroxene, this would be a low concentration here. Okay, and that behavior is reflected in your LNKD diagram. So you can take again those concentrations and build the ratios, calculate the KT, take the logarithm of that, plot it against 1 over T. That will give you some point on this purple line here. Now, what the rock is doing, of course, is it's not sitting at some temperature and just forming. It is evolving. It is cooling down. It is cooling down, it is exhuming, a lot of things are going on there. So it is worth looking at this diagram to see what happens when you cool down such a rock. So again, so this is the autopyroxene and the clinopyroxene at some peak temperature. You have the concentration profiles given by these red lines here. As you cool it down, so as the temperature comes down to this green point here, what that means is this ratio, the iron and magnesium concentration of the minerals, must change, and that would correspond to this green point here on this LNKD temperature diagram. And when that happens, the interface, the boundary between the autopyroxene and the clinopyroxene immediately comes to the correct value that it should. However, to change the composition of the entire grain, you need to diffuse magnesium atoms, let's say, out of the crystal here, and you need to diffuse them inside the clinopyroxene crystal here. And that is not very fast. So what ends up happening is that you develop a compositional zone. So the boundary here instantaneously goes to this green concentration, but the concentration profile goes from the original value here down to the green value here. You get a sort of a curved line. But then the rock is not sitting around. Of course, it's cooling further, so it goes from the green to the blue value. The temperature drops even more. And when it drops to the blue value, then your LNKD has to be a different value yet again. And that is reflected once again here. The interface once again comes to the value that it should have according to the equilibrium relations. However, the diffusion is a little bit more than what it was in the green, but still the interior of the crystal basically has not seen what is going on the outside. So things are diffusing out slowly, and that's shown schematically here in this diagram. When you have two minerals, A and B, initially they have a yellow concentration for A and a blue concentration for the B. Once you start cooling and start forming some zoned crystal, you form here a diffuse boundaries. The green and the blue and the yellow begin to get mixed with each other. And so this continues on. You cool further, you come to the orange grain, and this is your orange KD that would correspond to that temperature. And then the boundary once again goes to the value it should, and the crystal is now even more strongly zoned, and the thing continues on. And if you drop the temperature even more beyond that, then it turns out that the kinetics becomes so slow that even the interface cannot react. So it just freezes right at this point. And today, the crystal that you see would give you this orange measured zone profile. Now, from what I've been telling you, it should be clear that this actually is a continuous tape recorder of what is going on in the rock. What it tells you, so let's go through this cycle again, putting explicit times on that. So let's say we start with the red one. We take 1 million years to go from the red to the green, so that point, another 1 million years to cool from green to blue, 1 million years to go from blue to orange. So I have a total of about 3 or 4 million years time during which these atoms can diffuse. And that would give me one particular kind of diffusion profile here. If I cool the same thing very slowly, so I go through the same temperature, but at different times. So the gap between the red and the green is now, let's say, instead of 1 million years, 10 million years. And from green to blue, you have another 10 million years. And from blue to orange, you have another 10 million years. So the whole thing is, let's say, 40 million years. Then obviously, these atoms here have much more time to diffuse, and the concentration profile that you measure will be completely different. So that now gives you a tool to not only measure the pressure and temperature that the rocks have seen, but also how quickly the temperatures changed. So do we see that in real rocks? We do. So these are now data from the Quark Massif. And what you see is a concentration profiles. These are all the circles in each one of these panels are measured concentrations in a garnet autopyroxene pair on the left, top left, a garnet biotite on the top right, garnet clinopyroxene in other diagrams, And I'll show you on the right what the situation looks like. So in real physical pictures. So you see, this is a backscattered electron image again. You see the garnet biotite contact. So this is about where you measure such profile. You see that the garnet is zoned and the biotite is not. That's because in diffusion in biotite is usually quite faster. And you see that in this right image here, where you have a element concentration map. So that's the colors show you how much magnesium is in these particular places. And the brighter the color, the more towards red or lighter colored means higher concentration of magnesium. The lower the magnesium concentration, the darker the colors. And what you see immediately in the garnet is, it's pretty much the same composition, this blue color everywhere, excepting when you go really close to the biotite, there's sort of a dark blue rim that forms here. And that is where you measure these concentration profiles. So the same sort of thing you can get between garnet and clinopyroxene. This is a picture of an area. So you see that the zoning is actually very close to the rim. So you have to be careful to measure really close to the rim. But if you do that, you see here, for example, now the clinopyroxene is the one that's zoned, the garnet is not, and so forth. So what one can do is try to model these things using these diffusion coefficients if you know the diffusion coefficient. And that is the big problem, because these things, the timescales I've been talking about, are 1 million years, 10 million years, and so forth. How do you measure something like that in the laboratory? So what I'll do now is leave this thing here, recognize that there are these measured zoning profiles, which we can model in principle to get cooling rates or timescales. But first, we need to know how fast do these elements diffuse in these minerals, garnet, clinopyroxene, orthopyroxene, and so forth. So this is the problem. So the challenge that we have now is we want to study something in the laboratory that happens over millions of years in nature. And now it turns out that diffusion has this relationship that the diffusion length, S, is proportional to the square root of dt. Now, what that tells you immediately is that if you have a certain diffusion coefficient, certain number there, now these diffusion coefficients depend, there are properties of minerals, so they depend on pressure, temperature, things like oxidation state or how much water is around and so forth, a number of different things. But for a given set of such environmental variables, you have a diffusion coefficient, then the distance is proportional to square root of time. And what that means is to get the same diffusion coefficient, you can either look at large distances. So this is an example of an olivine from a meteorite, where you have zoning formed by diffusion over about 100 millimeters, and that for the particular pressure, temperature, and so forth that was relevant for this olivine took 100,000 years. Okay. Now, by this relationship, what you see is that if you could measure concentration gradients of 100 nanometers, you could see the same diffusion in 36 days. So the trick here is to work such that you keep the diffusion coefficient what you want to get, but you reduce the distance scale, you move down to nanoscales to see things that happen in the nature over micron or millimeter scales over millions of years. So how do you do that? So this is where we have a piece of equipment. This is an image from our lab in Bochum, a thing called the pulse laser deposition of thin films. So what you do here, I'll show you in detail in a minute. What you do here is you take a mineral or a crystal or whatever you want, you shoot that with a laser, and that converts the material to a plasma and deposits a thin film of that material onto a substrate. So let me show you how that works. So this is now the equipment looking, so this is the laser port. So an excimer laser comes from here through this thing and enters this sample chamber here. Now that excimer laser is actually exactly the same material that you use in many laser ablation ICP-MS equipment. So for those of you who know how that works. So now if you look at the inside this chamber, what goes on is this. So this is your laser coming in and hitting what we call a target. So you see a real picture of that here. So this is where we put whatever you want to make a film of olivine of a particular composition, a garnet or a melt or whatever it is. And then on the bottom, you have what are called substrates, so little crystals on which you deposit this film. So this is shown here. And this is shown that we heat this chamber a little bit before we do all this deposition, because the surface of any material always has absorbed oil and water and things. So you need to get rid of those. And so just to put the things in perspective, you see the whole picture here again on the right. So the laser beam is coming from the left. You're looking at the inside of the deposition chamber here. On the right is a control unit with computers and so forth. So once you turn on the laser, what happens is this here. So this is now olivine crystal of a particular composition that is being targeted with the laser. This green thing is olivine plasma. So the magnesium, iron, silicon in olivine has been converted to ionized state in a gas thing, and this then deposits that film onto whatever surface you have here. So what that looks like is something like this. So the olivine crystals, for example, mantle olivine phosphor at 90, we take cubes about 1 to 2 millimeters in size, and then we deposit a thin film on that of only a few hundred nanometers on size. And the whole thing works because there are two things that has happened in the last 20 or 30 years. We can manipulate material on nanometer scale, we can deposit such things, and we can measure them. We can measure concentration gradients using a variety of techniques. For example, secondary ion mass spectrometry, depth profiling in that, or we use things in an accelerator, very commonly in Bochum, which is RBS, which is Rutherford backscattering spectroscopy, or NRA, which is nuclear reaction analysis, and so forth. Now, what that leads to is what's shown on the bottom right. So if you have a diffusion coefficient for some element, some number, let's say 10 to the minus 21 meters squared per second. Now that may operate in nature and give you a profile over 10 micrometers in 200 years. And over several millimeters in your thin section in several million years. But in the lab, you can get a profile over 10 nanometers in 2 hours. And that's what really changed the picture, because what that means is you can basically set up such an experiment and go to lunch and have a long lunch and come back and your experiment will be done and you can measure the thing and get your diffusion data. This is what the things look like. So this is now thin film again of olivine and olivine. I just happen to have a lot of pictures of those because we've worked a lot on olivine. So this is now your phosphorite 90, the dark thing here is phosphorite 90 olivine, on which you have produced about 100 nanometer thick film of an olivine of a different composition. So this is now 2 olivines forming a diffusion couple, just like you were seeing the 2 pyroxenes before, or the garnet and pyroxene and the garnet and biotite and so forth. And if you look at this thing from the top, you see absolutely nothing. So this is a very flat, very top material. Now I should mention that this is used quite commonly in material science. So this is an example of the kind of thing material scientists do in indium and gallium zinc oxides on plastic materials. But in geosciences, this is done only in the lab in Bochum, and that's why we're able to do these things, and people come from all over the place to use the facility in Bochum. So I'll just show you what kind of data we get here. This is now diffusion coefficients of iron and magnesium in clinopyroxene as a function of temperature, going from 1200 degrees down to 800 degrees, that we published in this paper, Muller et al. In 2013. And that is one of the sets of numbers that we'll use to look at our samples in Quark. Okay, so with that, back to Quark. So this is now a picture that you already saw. You saw your garnet and biotite, and you measure a concentration profile across such a boundary here. You've seen a little more clearly here, this deep blue region where you have a lower magnesium content. And you have the temperatures that are worked out. So this thing is cooling from about 750 degrees to 520 degrees. When you model that, you'll get the cooling history over that range of temperature. And this is an example of what it looks like. So the circles are now measured points from an electron microprobe, and the lines are the calculated fits that you get by fitting such a diffusion model to the data. Now, what does that tell you? It tells you that this cooling from 750 to 520 degrees happened in 7.5 million years. And the cooling rate was about 30 degrees centigrade per million year. Okay? So you can go and do this with all the other minerals, or let me make it more clear. Completely did this for all the other minerals. And you can, as you see now, there's the same picture really that you saw before, where you can fit all the profiles quite well. However, to do the whole thing, you need a more complex thermal history. So you need a 3-stage history. What you need is a cooling from 800 degrees to 485 or 480 degrees centigrade at that 30 to 50 degrees centigrade per million year. This would be corresponding to cooling from the M1 metamorphic event. Now that is followed by a rapid heating again to 720 degrees centigrade over only a half a million year. And this would be correspond to the stage where you form that second garnet, the garnet 2. And then it cools down again from about 650 degrees at the same rate, roughly it turns out 25 to 30 degrees per million year. So overall, the cooling rates for these different stages are always between 25 and 50 degrees centigrade per million year. Okay. Now, what does that do to my picture? So I had this picture initially that M1 at 3,100 million year, M2 at 2,400 million year, and then cooling down. Now, what that told me was that for the initial piece of this history, if I connect the dots with a smooth line, the history was one of very, very slow cooling. It's actually quite difficult to imagine how you can keep something hot for about 700 million years without doing something. Now, this cooling rate, this continuous tape recorder tells us that it is actually something more complex. So what happened was we started from that temperature with some uncertainty in depth, some uncertainty in time, as you see here. So 3,100 to 2,700 million years, somewhere thereabouts, about 3,000 million years. But then it cooled down and sat at a much lower temperature for about 500 million years until it was heated again quite rapidly to this second stage here, and finally cooled down again at about the same rate. Okay, so this is now in pressure and temperature. So if you want to look at it more in a image that you can relate to, you can look at depth against time. So what you have on the left, you have the same picture again, but on the right-hand side, you see pressure or depth as a function of time. And you have this initial stage, considerable uncertainty, but that's where we were about 3,000 million years ago. That was followed by some exhumation, not all the way to the surface most likely, but somewhere at lower temperatures and pressures. And then it got heated and buried, a little bit buried, but heated mostly, to the second stage of thing, and finally got exhumed. So this is now not one smooth continuous curve. This is happening in pulses. So if you go back to our original diagram that I show on the inset on the top left, you have the blue circles, but between that now you have a tool with which we can work out these little episodes, these little pulses here. So that then is the story from this one set of rocks in Kurg. And the question then, of course, comes, well, how typical is this? I mean, is this something strange and bizarre that happened in these rocks in Kurg, or do you see this more often? And the answer is you see this more often. So this is actually one of the first works where we did in metamorphic rock with Shantanu Bhomik in IIT Kharagpur. And this was on the Central Indian Tectonic Zone. And again, you're looking pressure, temperature, but on the right, you see temperature, time, history. And you see, again, not a continuous cooling, but pulses. And these were, again, confirmed by other data from circumdating and so forth, that this is consistent with the results from other sources of information. So these are now all Precambrian rocks, pretty old rocks. The question is it also true of new rocks? Do you see the same behavior in new rocks as you? And you do. This is now another study, another set of studies that we did on the Himalaya rocks in Sikkim. And this was a number of different people who were involved in there. Some of them you'll be familiar with and recognize. Nilanjana Sarkar, who is now in Trivandrum, Dilip Mukhopadhyay in Roorkee, Somnath Dutt in IISER. Well, I still think of him as Jadavpur, but whatever, and a number of other people from elsewhere. And again, what you see is that the evolution was not one continuous exhumation from the peak temperature or the highest depth of burial, but the evolution was in pulses. And these are all metamorphic rocks. Now, I began this talk with talking about geological history, and which is a lot bigger and broader than metamorphic rocks. So the question comes, okay, so this may be something not just in Ruhr, maybe in some wide range of metamorphic rocks, but do you see this also in other kinds of rocks, other kind of behavior? And the answer is, of course, yes. So I'll take some time to take you through this slide here. This is now completely different. This is not metamorphic rocks at all. This is now volcanic rocks, so the other extreme. So we still have high temperatures, of course, but even higher temperatures, in fact, but no pressure. So this is things at very shallow pressures or near the surface. And this is a set of studies that we did on the Mount Etna, which is a very active volcano in Sicily, in southern Italy. And so it's continuously erupting, and we looked at the eruptive products from 1991 to 2008 that you there were a series of papers, but this paper that I show on the bottom right of the screen is a Journal of Petrology paper where we summarized results from everything that we got. And what happens there is the mineral changes, but the behavior remains exactly the same as what we were talking about before. So what you are now looking at is olivine. And again, during this magmatic evolution, olivine grows in different pulses. And once you have different growth zones, things diffuse between those zones at those high temperatures. That's shown here on this concentration profile diagram. And you see it much better on this element map here. This is again the magnesium concentration in olivine crystal from such a lava flow. And what you see immediately is that it is not one smooth continuous change. So in the middle you have quite high magnesium, reddish orange. Then you have a rim with something yellowish, so it's decreasing. Then it goes to green and then to blue. So it seems to happen in kind of pulses with diffuse boundaries between each of those regions. And that got, so there was a lot of such crystals that were modeled. I actually remember the number. There were 180 to 190 such crystals that were mapped, studied, and modeled in detail. And what the picture that came out of that, combined with a lot of thermodynamics to get the pressures and temperatures and so forth, something like this. That so now you're looking at really only the very shallow part of the volcanic history. So these melts, these are basalts, these are coming from the mantle, and we are not looking at the history from the mantle to the shallow crustal reservoirs. We're looking at depths of 15 kilometers or so. So this is really the upper crustal history of this magma before it erupted. And what you see here is that about 1.8 to 1.6 years before eruption, it was at depths of between 10 to 15 kilometers. Then about 4 months before eruption, the magma moved up to a shallower depth, like 5 to 7 kilometers, and stalled there. Then about a month, 40 days before eruption, it moved up to the really shallow level below the volcano, and then it erupted. And during this stage, it was continuously degassing. So what you see is that the water fugacity, or the water content in the melt, decreases continuously. So once again, this is now very different setting, a volcano rather than a metamorphic rock, very different timescales, years and months rather than millions of years and billions of years. And you still see that the evolution is not the simple picture that you have of a magma chamber and then things come up and erupt, but things start moving and then they stall and then they move again and then they stall and finally they erupt. So, and that's incidentally being found in many, many different volcanoes all over the world. So this is, again, not something specific to one particular volcano in Etna. It is just general behavior of such volcanic systems. So with that, let's go back to our original question. Uniformitarianism versus catastrophism. Do we have long timescales or do we have short timescales? I hope what I've shown you is that we have long and short timescales. Geological events are continuous, long. Some are very episodic, like the volcanic eruption at the very end of that cycle in Mount Etna. And you have everything in between. You have, in Mount Etna, you have things on timescales of years, months, weeks. In the metamorphic rock, you have timescales on the 500,000 year or 1 million year, and then the whole evolution over several 100 million years. So what you have is a hierarchy of timescales. You have the whole spectrum between long and short. It's not just either or. So that's the main message of this talk. But before I let you go, I want to touch on one final point here. Now, if I'm saying all of this here, what about all the pressure temperature histories that everybody calculates, all the papers that you read where the pressure temperature curves are smooth curves? So let's just go take a look at that again. So this is another one of our studies from Sikkim again, looking at some garnets from the famous inverted metamorphic sequence, and it's particularly relevant and gives me pleasure to be able to talk about it here because the inverted metamorphic sequence in Sikkim was first reported by SRI. And actually, it was also one of the first reports of inverted metamorphic sequences at all anywhere on Earth. So now what we did with Fred Guidis is an extremely detailed pressure temperature path diagram. So what you see next to so what you see now on the left is a picture of a garnet. And this is now concentration of manganese in the garnet, which is again zoned. Here you use diffusion in a different way, actually, which I will not get into. But you combine that again with thermodynamics, and that's your phase diagram, which is very complex in the middle. But when you do all of that, what you end up with is a pressure temperature path that's shown on the right panel. And this is kind of a sharp history where you increase pressure and temperature and come back along roughly the same path. So the three lines are for three different samples. There's slight differences in pressure, but if you take any one of those, you just go up here and you come down here, and that's a smooth curve. And in this case, because it was in such detail, we know that we actually followed that smooth curve. There were no spikes in between here. However, what I want you to look at is the scale on the axis here. So this is now from 4 to 5.5 kilobars. So this is a tiny part of the history. And the temperature is going from 525 to 575 degrees centigrade. So if you take that and put that in a bigger picture, which we did in a review article that we finally produced, all of us together, you see the situation here. So on the left, again, you see the pressure temperature path that you have worked out from a lot of work from those garnets. And when you put that in an overall picture of the crustal evolution from 0 to 10 kilobars and 0 to 800 degrees, that whole history is the tiny red solid line here. And you don't even see the retrograde path here because that's just a small blip in here. And the rest of the dotted line is something that you need to get from somewhere else. So a very important message is that any tool that you use, in this case, metamorphic petrology, gives you only a very small segment of the overall geological history of the rock, not to mention the whole crust. So to get the entire history of a system, you need to combine many different tools. And we tried to sort of illustrate that in this kind of messy diagram in another review paper that we wrote in Lithos. So if you have a pressure temperature history of some rocks, the two lines are shown because the particular paper dealt with Himalayan rocks again. But the main point I want to make here today is that there are different tools that we have. So for example, you can use phase relations, uranium-lead dating. That will give you some information about the prograde history maybe here. Then you can get peak temperatures also from thermodynamics, and then you can get cooling rates using the diffusion data that we sort of just talked about. Then you can look at deformation textures and structures in ports, but those get frozen at a much lower temperature down here somewhere. Then you have other tools like argon-argon dating that will give you even lower temperature information. And finally, you have things like fission track or uranium, thorium, helium dating, and eventually actually going all the way up to sedimentary data, geomorphology, and active tectonics. That gives you the very last pieces of the exhumation history. And it's really all tiny pieces of the jigsaw puzzle that you put together, and any one of these tools gives you only a very, very small segment of the whole history. So with that, I'll leave you with some final messages. So the first and the most important message from this talk is that the geological processes are pulsed. They're not continuous along any particular path. They occur on a hierarchy of timescales, so they're neither very slow and long and continuous, nor always very rapid and episodic. You have the whole range in between them, from very short to very long. And finally, any one tool captures only a very, very small segment of the geological history. So you need multiple tools and an interdisciplinary approach to really work out the geological history of any particular area, any particular age, any particular terrain. That. Thank you. I'll end here.
Yeah, thank you so much, sir, for this interesting lecture and telling us how we can use different tools to understand the time scales of the different geological processes. So before going into the question and answer session, I would just like to mention a few things. So there is a raise your hand option in the menu tray. If you have any question, please click on that option, and whenever we will call your name, you can just unmute and ask your question directly to the speaker. However, if you cannot find that option, I request you to pose your question on the comment box and I will take it to the speaker. And if anyone here is viewing us on YouTube, please directly write the question in the live chat box and I will surely mention it to the speaker. So let us just take a 2 minutes break before we compile all the questions. Okay, in the meantime, I would like to mention that the 98th annual general meeting of the Department of Geology, Presidency University will be held on 24th of September 2021. And on that day, we will have among us Dr. Shomak Rai Chaudhuri as a guest speaker. And we will share the details of this event later via email. Okay, so if anybody has any question, they can just unmute the mic and ask it directly to sir. Anybody?
Yes.
Yes, sir. Sure, sir. Abhinav sir. Oh, Dhruva sir as well. Yes, sir.
Sumit,
Hello.
can you hear me?
I can hear you, sir.
Yes. So your talk has thrown me into a philosophical dilemma, that how much is the reality dependent on the scale of observation or scale of consideration. For example, if you look at a photograph, one scale, it is a nice photograph, When you go on enlarging it, then it is got disrupted into individual pixels. So what is the reality? Is it the pixel or the combination when the pixels are fused together to form the photograph?
Well, that is exactly the point. And I think both of those are the reality, because you do have the pixels. And if you look at on a proper scale, then you have the pixels that are put together. And however, if you want the big picture, then the pixels need to be arranged in a particular manner to produce the overall pattern of the whole picture. And yes, so we need to, one of the things that we should always be aware of, I think, is that no matter what scale we look at, maybe other than satellites, we're always looking at a very small spatial scale. So we can, going down to nanometer scales, we can look at thin sections on millimeter scales, but we can go to the outcrop on meter scales, or even maps on hundreds of scales. This is still, compared to the whole world, it's a small scale. And the time scale of any one thing is also quite small. So we are always trying to put together a picture from tiny pixels. And the pixels themselves are of different size, I guess. That's the point. That's my philosophical answer to that one.
So, so what you get out of your exercise, is it valid only for that scale? That was what my point was.
No, what you need to do, so that was why I put in this last part of the talk, that it is like tiny, so so again, to stick to the pixel analogy, so the pixels need to be put together in a proper pattern to get the picture. So any one will give you a thing that's valid on that scale, but to get to the larger scale, one needs to put them together in a manner that's consistent to get the whole picture. So for example, to get to the curve example back again, if where let's say are correct, I mean, this is still being reviewed, so we'll find out what the reviewers say, but let's assume that those are the right numbers. But then the question is what happened in between. And if I assume that there was a continuous evolution from stage 1 to stage 2, that would give me a very different tectonic picture from, if I say that it cooled down and then it got buried again, because then you need to do different dynamic and different structural things to make those processes happen. And that's when then it becomes a question of looking at the structure, at the dynamics of it, things that you would know much more to see if those are consistent with such an evolution. And that's why we need to take the petrology, we need to take the geodynamic modeling, we need to take the structural evolution, and then see that they're consistent with each other to produce an overall big picture.
Thank you.
Obhinav sir, you were asking some questions. So,
actually, it is actually not a question, because I'm not competent to ask a question to a stalwart, and I'm learning. Let me first congratulate him for his excellent talk, and I'm very much educated through his talk no doubt. And just a query I just like to ask, and you just discussed 3.1 billion years, the M1, then the M2 is a long gap, and you gave the residence period of 500 million years. Then suddenly again there is a rise of heat, I mean increase in the heat, again it went back. That means the heat is input. The reason for that input must be found in the field or something. What could be there? That is a very important thing. And also the fabric changes is in the matrix of this garnet should be looked into that. I feel it, so that overall geology, the structural aspects must be compiled, I mean coupled with these observations to justify this is the residence, and then again there is a heating coming back to the path, again it is going down.
Thank you. This is a very good question to have. So let me answer in 3 pieces. First of all, it's very interesting to hear you call me a stalwart, because when we were students, we used to think, oh, wow, Abhinavada correction, key correction. So it's really, really strange to say this.
Don't embarrass me. My guru is here, Professor Mukhopadhyay. He must be laughing.
You remain Abhinavada. So the second question, yes, absolutely. I take the question in two parts. So one is there must be a heat source that causes the thing to heat up again, and the other part is there should be a signature in the structural data. Now, the heat source, there are actually ways that suggest that it can happen, and actually it should happen. So this is a whole different part of the story that I didn't get into today, but we worked on, is how the geodynamics looks like in these early Earth situations where you have much hotter mantle than what you have today. And very basic terms, what happens is that because the Earth is hotter, the viscosity of everything is a little bit lower, so things tend to flow more. And it turns out that if you do a plate tectonic modeling, and then it becomes a question of many different issues. So when did plate tectonic start at all? But if you assume plate tectonic was there at that time, then it turns out that the plate tectonic behavior would be very different from what it is today, because you have a much more soft plate compared to the more rigid plates that you have today. And if you do the models in those settings, it turns out that you do in fact produce such pressure temperature histories. So that's one thing, that there's a feasible thing. The second thing is that the second garnet forms because of clearly because of some kind of a fluid melt related activity. So whatever that is, that needs to be looked into and studied more. And the third question was related to the structural setting. And yes, there should be structural signatures of that, and that is for someone like you or the structural geologist to look at. I hope that the signatures will be consistent. But the one thing that I like to point out, and that was the reason I touched very quickly on the quartz textures in the last slide, is because if you are going through such a history, then quartz tends to recrystallize quite quickly. And so the signatures you see, for example, in the quartz texture, may be defined more around 400, 500 degrees. And so it may have lost the memory of whatever happened at 600, 700 degrees. So that's something that needs to be looked into, keeping in mind this behavior of these materials. Yeah, so done that way, the textural, structural information has to be consistent with what you're saying. If not, then we need to redo the picture, of course.
Thank you. Thank you very much.
Okay, so I think we can discuss a few more questions. If anyone has any comment or question, he or she can directly ask it to sir. Okay, so I don't think so that anyone has a question, sir. So
can I just one thing?
Yes, sure, sir.
The problem I feel, which we often encounter, that when you approach the reality from different points of view, for example, say you are looking at a rock from the metamorphic petrologist's point of view, and looking at the rock from the structural geology point of view, their scale of resolution is often different. For example, you can, with your diffusion, say you can detect differences over nanometers. But often in structural geology, we do not recognize differences over such small scale. So how to get over this type of problems when your scale of resolution is different in different disciplines? How we can combine them to arrive at a holistic picture?
This is it's very important. And this is why one of the pictures that I use in many of my talks, and I did not today, is that I think this poem that we learned in school, 6 blind men of Hindustan, they look at me. And I think that picture should be hung up on the entrance of every geology department in the world, because that's a problem we all have to deal with. Now, the thing about the scale, though, is that what we are measuring in the garnets and the pyroxenes are on the scales of micrometers or even nanometers, but we can apply it to a much larger scale because we can sample things from a much larger area, of course. So if I go and, let's say, take 10 samples from a 1 meter outcrop, and I get the same story from this 1 micrometer from all of those, then it's reasonable to say that that 1 meter outcrop experienced that same history. And that's actually something that works out that way, because there have been times when, actually one example was in Sikkim, where you go and do that and you find all of a sudden there's a discontinuity somewhere. So the two things that looked otherwise completely similar have had a different thermal history. And so then that's how we kind of build up the spatial hierarchy, that you observe on micrometer scale, but you take samples from 1 meter outcrop, and then you take samples from many different outcrops. So then you have a kilometer scale map picture and then expand that on. So that's one way of moving up and down the scale, by just using more samples and more reproducibility. We should continue this discussion because this is a very basic and fundamental discussion. So we should find ways to meet and continue this on.
Yes, Prahlada, you can ask the question now to so.
So thank you. That was very motivated talk, sir. I was just curious to know about the tectonic scenario that the rock have experienced. That the M1 phase through M4, the rock is being cooled and then it is being heated again, right, sir?
Yeah.
So
Cooled. It's going through a few pulses. Yes. Mm-hmm.
So what would be the tectonic scenario, sir? Is it indicating sort of accretionary orogeny?
No. Okay, so let me see if I can show you one quick thing. So let me try to do this because I have other slides, but I don't have things ready, but I'll just show you one picture here. So do you see my screen now?
Yes, sir, yes.
Okay, so what it is showing on the left is this pressure temperature history, this pulse history that you're seeing. And on the bottom, what I'm showing are sketches, but these are based on geodynamic models of what a collisional orogeny would look like at different points in the history of the Earth. So you're starting from Archean on the left and going to Phanerozoic on the right. And what goes on is basically what I was just saying in words before, that the Earth is cooling, or was cooling at that point quite significantly. So the cooling has slowed down a lot more over time. But from Archean to at least mid-Proterozoic, there was quite a substantial cooling of the Earth's mantle, and that affects geodynamics. And what you see here on the very left is that the plates, even from the sketch here, looks a little soft, like it is almost like you are trying to collide a soft wax rather than a piece of wood. That's one way of I think about it. So if you go to the right, if you look at the more Phanerozoic current day picture, you have rigid blocks of wood kind of thing that are not wood. Rheology is more complex, but in a relative scale, and they tend to break, and then you have events like slab break-off and things and collision. But in the hotter mantle, what happens is when they collide, they because they're softer, they tend to move back, and what we call peel back tectonics. So they move back, and then of course the overall geodynamic force makes them collide again. So that leads to this situation of where you have a burial and then exhumation, and then burial again and exhumation, because these slabs here are colliding and then moving back, colliding again, because the things are quite soft at the time. So that's one explanation that we have. There's a lot more that needs to be done to do that. But the main point is that because you have this peel off, hotter asthenospheric mantle comes up here and produces hot conditions in this region here for quite long times. And that's a behavior you would not see in more modern day tectonic settings. There's a different paper I wrote with a student of mine where we looked at the thermal history of metamorphic rocks from over the entire geological history, and there seems to be some systematic that supports that. So to answer your question in one line, so the setting such as an accretionary origin would not have existed exactly in that form during the Archean Proterozoic, because the Earth was hotter. So it is a somewhat different setting from the things that you see today in a plate tectonics. That is my bias.
Thank you, sir.
I think Dhruvo sir again raised his hand. So do you have any comment?
No.
So can you hear me?
No, I think that was a mistake on my part.
Okay, so.
I also see a hand from a PG. Oh,
that's Pradada. Yes, that's Pradada. Okay, so I think we are at the end of this program. So now I would like to call Ms. Debarati Saha, Secretary of the Geological Institute, to present the vote of thanks. Debarati, the mute. It's in mute.
Thank you, Ankan. Good evening, everyone. It gives me pleasure to deliver this vote of thanks today. First and foremost, I would like to thank Professor Sumit Chakraborty, who, despite his busy schedule, has found time to grace this event. Thank you so much for such a fascinating lecture. As we are eager to maintain this relationship amongst us, we are grateful to our respected and beloved alumni whose participation in this lecture was crucial to us. We appreciate that despite the busy timetable you all have, you have managed to attend this lecture. It means a lot to us. I would also like to extend my heartfelt gratitude to all our faculty members who have guided us to make this event achievable. I am thankful to all the participants for attending this lecture and for their enormous cooperation. I am thankful, but last but not least, I also take this occurrence to thank the entire committee of Geological Institute whose efforts have made this event possible. With this, I end my speech. Now, I will request everyone to turn on their camera so that we can take a screenshot to preserve this memory. Everyone, please turn on their camera. Thank you, everyone. Hope to see you all again as we meet on 24th of September 2021 for the 98th annual general meeting of our department. Till then, please take care and stay safe.
So big thanks to all of you, sir, who were present here. and the session is open to everyone. Like you can chat or do anything. So you can go back to the past and nostalgia and has anything else.
We'll all have a cup of tea by ourselves, like we used to have after the end of the Professor Rai Memorial Lecture. This time we'll have it on our own.
Yes, sir. I remember tea used to be served just outside the gate of OLT, and we all used to like.
I hope next year we can do it in OLT.
Yeah, sure, sir. We all also hope so.
It's good to see everybody here because over now you get to see more people through this Zoom thing, team thing these days that I've seen for many years. I've seen people now that I've not seen for 40 years. So very good to have everybody here.
So I think we can end this session here. So the participants may leave if they want to.
I'll go. Arkadaşlar, we have to continue this discussion. Thanks.
Goodbye, Sumit. All the best.
Thank you, sir. Bye.
Thank you, sir.
Thank you so much, sir.